Hi, guys. Oh,
Hey, how you doing?
hey, Chicken Wonderful. Just happy to be here. Okay, yeah, let's admit all. Hi, Blake. How's it going for you?
It goes, sir. Just got off work.
Great, great. Do you remember where we ended last week? Or
Um, I want to say maybe right before the conversions, I want to say.
right before the metric system?
Yeah, honestly, I don't recall.
Okay,
Sorry.
nope, not your fault. Okay, I think I need to do, oh yeah, that's the right. That's not that. Okay. Guys, I was really impressed with what you were doing in the discussion forum. You're using it for what it's supposed to be used for. A couple people uh, put up some questions. One was about chem and physical properties, and the other was about how to convert miles per hour to, or centimeters per second to miles per hour. Anybody, is the person that wrote that question, are they in yet? Nope. Nope. Or nobody wants to admit it. All right. Good enough. Oh, we getting along okay? Yeah.
Don't forget
Questions
to
be
talk about
expected, right?
disability.
Okay, PowerPoint.
Don't forget to talk about disability.
Yes, thank you. Thank you very much. I am just lost my presence. Oh, there it is. Thank you. That's the one I wanted. Let's get. I'll come and get it in a second. Name that change I'm going to need. Okay. So, I apologize about the quiz, ladies and gentlemen. I apologize about that because basically, I have to change it. It's not fair to you guys who are having this meeting at 5 o'clock. If I give the quiz and let it stay open till 5, that means the people that have the Zoom meeting in the morning are going to have the advantage of having had a lecture on the material. So that would put you at a disadvantage. That's why I have to put the time at 9 o'clock. I'm sorry.
No problem. Thanks for the change.
Any questions? Guys, the other thing is, look at the announcements. Starting this week on Sunday, I'm going to put in the announcements the times and the assignments that are due that coming week. Fair enough, guys?
Sounds good.
Okay, let's see if I can find where we were.
I have a quick question about the quiz.
Okay.
I was confused on two of the questions.
Okay.
One of them was about propane combining with oxygen to make water. Why is that not a chemical change?
Okay. Let's look at it. Let's see, stop share screen. Now I got to figure out. See the screen? Rebecca?
Yes.
I'm sorry, Rebecca,
Yeah.
you're asking the question, right?
Yeah.
Okay. Don't tell me I made a mistake, Rebecca. And don't tell me I have to give you another point.
I don't know. I could be wrong.
Well, from my point of view, let's hope you are. Because if not, I got to go regrade all these silly things. Okay.
I'm willing to learn.
Okay. Add edit
Is that one
questions.
question 5?
Question what?
5.
Okay. The answer is a property. I'm going to get into this a little bit today. And you have to look at the way a question is worded. Now, as you read that, Rebecca, as you're reading that question, did it happen?
No.
It
Oh,
didn't
okay.
happen. That means
Okay,
it's a
gotcha.
property and not a change. Does that make sense to you?
Yeah, it does.
And we are going to get into that. We're going to get into that today. Okay? And sorry, my organization here leaves a lot to be desired.
I also had another question. I was
Okay.
really confused on the true or false question.
Okay. Which one?
It was like leaders to
Oh,
yeah,
this
the
one.
7th one. Yeah, I have no idea what that's asking still.
All right. You have 1.057 quarts is equal to 1 liter. 4 quarts equals a gallon. Okay? 4 liters is smaller than 1 gallon. Okay? Rebecca, is a quart bigger than a
Yes.
liter?
Yes.
Okay, so if you have 4 liters, right? That
Okay.
means that the quantity thereof is going to be big. It takes more quarts to make a liter, right? So
Yeah.
if you have 4 quarts, that's less material, that's less volume than 1 liter, than 4 liters.
Oh, I just realized what the question is asking. The question is saying that 4 liters are smaller than a gallon. You say, okay. I was really confused about how it was formatted. Never mind. I got it.
All right. Anything else, guys? Okay, now let's figure out where we were. We were somewhere in calculations, right? We'd gotten through, I got through this, didn't I?
We just finished through the multiplication and division part.
Ah, okay. Ah, that's right, because Rebecca corrected me. Right, Rebecca? You were right. That last question, if you multiply 3.68 by 5, the answer you get is 18.4, but there's only one significant figure. So that comes to 20. So you have 20 plus 4.2. That leaves you 24.2, but there's only one significant figure. So the right answer for that last one is 2.0 times 10 to the first. Or if you want to do it the archaic way, 2, 0 with a line over the 0. So basically, is this where we came to? Is this
Yeah,
where
I
we're
think
at,
so.
guys?
Yeah.
All right, this is an important slide. This is an important slide because you're going to use this a lot when you're converting grams to moles and moles to grams. What you want to do is you always want to choose a conversion value that doesn't limit your data's sig figs. So if you have 3.251 quarts and you want to change quarts to liters, then you want to choose a conversion factor that you're going to multiply by 3.251 by so that you don't lose the fact that you have 4 sig figs here. If you multiply it by 0.95, your answer is going to have 2 sig figs. Not a good choice. 0.9463, again, you're losing sig figs. You have to choose a conversion factor of at least 4 significant figures in order not to lose sig figs. Can you use one with 5? Absolutely. Can you use one with 6? Absolutely. So we got to make sure of how many sig figs are in our conversion factors. If it's an exact number, you don't need to worry about it. Because if it's an exact conversion, then the number of sig figs are going to be what the data is anyway. So if we're dealing with methane, 54.60 grams of methane. Rebecca, which set of atomic weights, atomic masses do you use? Rebecca, how many sig figs is in your
Yes.
data?
4.
So you want to make sure that when you do your molecular weights, that the molecular weights each have 4 significant figures. So which set are you going to use?
On the carbon side, use 12.01, and on the hydrogen side, use 1.008.
There we go. You do that, you won't limit your sig figs of your original answer. Okay, scientific notation. We're going to do this real quick, guys. It's going to be extremely useful for you, if not necessarily this semester. Next semester, you're going to be working with huge numbers and very, very small numbers. So you're going to need scientific notation to do these calculations. And basically, any number can be represented as the product, in other words, the multiplication of a number that's between 1 and 10 and 10 raised to the power. So what you want is you want to look at your number that you're trying to convert to scientific notation. You want to make sure that it has only one integer to the left of the decimal. The power of 10 is going to depend upon the number of places the decimal is moved and in which direction. If the decimal is moved left, the power of 10 is positive. So if I want to get scientific notation of 345, originally the decimal is to the right of the 5. To get the 3.45, I have to move the decimal 2 places. So that is what my exponent is. Since I moved the decimal to the left, that power is positive. If on the other hand, I move the decimal to the right, say I have 0.0671, then I count how many places I've moved the decimal. 1, 2. So that's my power of 10. But I moved it to the right, so the power of 10 is going to be negative. I love the engineering system. It makes a lot more sense than this crazy times 10 raised to some power. Engineers use a big E with a number after it. The number that's after the big E stands for what power the 10 is raised to. So if we have e to the 12, that's times 10 to the 12. E to the minus 3, 10 to the minus 3. Guys, it's a pain in the butt for me to use the times 10 to the 12th. It's a pain for me to do that. It's a pain for me to stop that. It's a pain for me to do that because I got to write the X, the 10, and then I got to put a caret and the 12. So it's much easier to write e to the 12. So you will see a lot of these references in my quizzes and tests. Guys, if you don't laugh, I stop showing the cartoons. Thank you, Nathan.
Welcome.
Understand this, guys. If you don't know significant figures, then you've lost at least 250 points because of significant figure errors between the intro lecture and lab. Try to keep the points lost in 2045 to a minimum by learning the rules. By the way, I made up the 250 points. Are we good, guys?
Actually, I had a question.
Who is this? Dana?
Dana.
Dana. Okay. Hi, Dana.
So for the engineering notation, it's going to be times 10 to the 12. Like, I get that. But what would you do in front of it to show what you're
It's just
multiplying?
it's just the same thing that's in front of the scientific notation. For example,
Oh, okay.
I am going to eventually get out of this. Okay, so if I'm in here, so if I have a number, we're gonna put it in here as 4, 5, 6, 7, 3, or 2, okay? How engineers would write this is, they would write it as 4.5672 E4.
Okay.
Does that make sense to you, Dana?
Yeah.
Okay, that's how that works.
All right. Thank you.
Okay, hopefully, now I got to get rid of you guys. Okay. Yeah, it's in there, good. You see the new slideshow?
Yes.
Yes.
All right, this is the topics page is very, very small. Basically, you're gonna learn what physical properties are. Then you're gonna learn what chemical properties are. You're gonna learn what physical changes are and how matter can change from one state to the other. And you're gonna learn how chemical changes cause some kinds of matter to become new matter. Basically, what we're talking about are properties. And property is nothing more than a characteristic, a trait, an attribute. Thus, basically, when we're talking physical properties, we're talking about qualities of the substance itself. Now, when we're dealing with chemical properties, we're talking about the ability of the substance to transform into another substance. So we're talking about the qualities of that substance. The property that can be measured without changing the composition. In other words, in a physical property, the substance does not change. Basically, we're talking about the odor of something, color, what volume it has, what physical state, the solubility of the substance, density, melting, and boiling point. Ladies and gentlemen, physical properties are what allow us to identify chemicals. Because we're identifying a property, we can associate that property with that particular substance. Water boils at 100 degrees Celsius. Water has a density of 1 gram per centimeter cubed. These things help to identify water as being water. So if we can identify the physical property, we can identify the substance. So how do we detect physical properties? Nathan, how do we detect them?
See, hear, touch.
Are you cheating on me?
No,
You're not cheating.
I have my laptop here next to me, so I can.
Yeah. So you looked a slide ahead, right?
I did.
Okay. See, hear, touch, smell, taste. Guys, not so much taste in chemistry. We don't eat chemicals, but we do in a way. Jasmina, you there?
Yeah, I'm here.
Jasmina, hi.
Hello.
Hello. She's very, very happy to be called upon, I can tell. Jasmina, have you ever bitten into a lemon?
I don't think I've ever bitten straight into a lemon. No.
You're being really uncooperative, Jasmina. Dana, have you ever bitten into a lemon?
Like peel and all?
Yes. Or
No.
bitten into, come on, just bitten into a lemon. What's it
No.
taste like?
Lemon?
Yeah, it tastes like lemon. Oh my God.
It tastes sour.
Thank you so much. So, if I were to tell you that acids taste sour, what deduction can you make about a lemon?
It is an acid.
It's not totally an acid, but it contains acids, okay?
Okay.
So yes, this is the way we're going to look at physical properties to be able to identify substances. So basically, again, I've repeated the physical properties, but chemical properties are reactivity. It's basically making new stuff. If you digest sugar, eventually what happens? The enzymes in your stomach and your enzymes in your cell eventually turn that glucose into carbon dioxide and water. And when it does it, it also creates energy. So we've gone from a molecule of glucose to molecules of carbon dioxide and water. When steel rusts, we have changed the substance from iron into an oxide of iron. Basically, when we have a chemical change, the substance changes to a different other substance. Now, a chemical property is the ability of a substance to transform into another substance. This involves possibilities. You have to understand, if it's a property, it hasn't happened yet. So you got to read the questions carefully. Rebecca, sodium can react with water to form an explosion. Has it happened yet?
No.
So when you're dealing with properties, you got to kind of ask yourself, has it happened? If it hasn't happened yet, it's a property. If it has, then it is a change. It's the ability to make a new substance. If we've made a new substance, are we making, let me rephrase that. If we make a new substance, is it possible that the physical properties of the new substance are going to be different than the physical properties of the old stuff?
Yes.
Yes.
So I have salt. I have salt water. Salt, the sodium and the chloride completely dissolve in the water. Okay? I have another glass of lead nitrate. Again, clear liquid, everything's dissolved. I pour them both together and I get a solid forming. Before, the physical properties were such that everything dissolved. When I mixed them, I got a new property that I formed a substance that doesn't dissolve in water. That is a change. Does that make sense to you all?
Yes.
So if we go back to just physical changes, basically all that means is altering the form or state of a substance, but it stays the same. I have a piece of paper. Let's see who else is in here. I got 14 of you. Where are you at? Aubrey. Where you at, Aubrey?
Hello.
What can I do to physically change this paper?
Rip it.
Is this piece of paper different chemically from this piece of paper?
No.
Ming? Ming?
What?
Min? I'm probably saying it wrong. M-I-N-H. Are you out there? Put your mic on. Where you at, man? First of all, I want to know if I'm butchering your name badly. I know I am. Okay, man. We'll give you a break there. Jillian. Jillian, you out there?
Yeah.
Okay,
Yes.
what else can I do to this paper?
You can cut it.
I can cut, I just ripped it. Come on. Can't you be a little more
Around
imaginative than that?
You can crumple it.
Crumple it. Is this piece of paper any different than this? Are the molecules any different?
Now,
So I have a physical change. What else can I do to this piece of paper? Joseph.
You could burn it.
No.
Oh.
No.
Physical?
If I burn it, right? If I burn it right now, I have a compound that is a solid. If I burn it, I turn this cellulose into carbon dioxide and water. So Joseph, when I burn it, have I done a physical change or have I changed the chemicals?
Chemical.
If I've changed the chemicals, then it is a chemical change.
Okay, you can fold it then.
I can fold it. I can make a paper airplane out of it.
There you go.
Okay, I can do anything I want to it. And I got to go find myself where I'm at.
So even if it's a balanced reaction, it's still a chemical change.
It has to be a chemical, I mean, it has to be a balanced reaction. Eventually, we're not going to deal with unbalanced reactions. So if you can make a reaction, then yes, it's a chemical change.
Okay.
So basically, when we're dealing with physical changes, we're dealing with the way the substance looks. I just painted my house. So basically, I put a coat of paint on the gypsum drywall. Is the gypsum any different now than before I painted it? I've just undergone a physical change. So basically, what you're doing for physical changes, you're changing the way the substance looks. You're changing the shape, size, or you're coating or painting it. Remember, changes in state, going from a solid to a liquid to a gas, is always a physical change. If you dissolve something, you dissolve salt in water. You boil all the water away. Don't you get that white crusty stuff left back again? So dissolving the substance doesn't change it. Okay. On the other hand, when we do chemical changes, we get new stuff. Now, as I explained earlier, if we get new stuff, the new stuff has different chemical properties than the old stuff. That's how we tell that a chemical has been changed. You light a campfire. The log doesn't look the same before and after. There's a lot less of it. We've changed it. We have a chemical change. Let's deal with rust. Let's think about this. Joseph, what does iron look like? Have you ever seen iron?
Yes.
What color is iron?
Like silver, I think.
Yeah, silverish. It's kind of like a dull silverish color. What color's rust?
Brown.
So
Green.
we have a change in color.
Green.
All right. Have you ever tried to grab rust?
It's
What's the consistency of rust?
like,
Does it break off very
rocky.
easily?
Yes. Well,
What?
it's kind. I mean, it's like stains your hands. That's for sure.
Yeah. What about
But
iron? What
it's
about
like-
iron?
I
What
don't know
about
about
like
that.
a hammer? Is iron more solid than rust is?
Yes.
So you got changes in physical properties. If you have changes in physical properties, then you probably have a chemical change. So physical change, just changing the way something looks, changing its state or dissolving it. Chemical change, we're physically, the second time I did that today. Chemical change, we are changing the substance itself. Okay. Yeah, this stuff is not important. I should probably get rid of it. Elemental bromine is a dense, dark red, pungent smelling liquid. Is anything changing? Jillian?
No.
If it's not changing, is it a change?
No.
So it has to be a,
Property.
okay.
Physical property.
Well, let's ask yourself a question. Is it saying that it can react with anything? Or is it saying it can form something else?
No.
Then it is, as you said, a physical property. Nope, it's not what I want to do. Why do computers do what you want them to do? There we go. I gotta look my participant list up. Why did that go crazy? Oh, there we go. Sorry, guys. Don't know what happened there. Okay, you seeing the screen again?
Yes.
Okay, Jessica. You there, Jessica?
Yeah.
All right. We have, remember, we just said elemental bromine is a dense, dark red, pungent smelling liquid. I got a second scenario for you.
Okay.
Why is this doing this? Okay, I want to get these people up here. Okay, that's something. What just happened? No, I don't want that. Okay. Elemental bromine will react vigorously with elemental sodium metal to form a white solid. Now, has it happened? Who did I just ask?
How did this happen? Because it like chemically reacted.
Go closer. I can't hear you.
It chemically reacted.
Did it? Read the sentence carefully. Has it happened?
It reacted vigorously.
Look at the sentence. Did it happen yet? Will react. Has it happened?
Oh, okay. No, it didn't.
That's why you got to read these questions carefully.
Yeah.
It will react, but it hasn't happened yet. So is that a change or a property?
That's a property.
If it's a property, now, is it saying that I'm going to make new stuff? Look, remember, the stuff that happens is I form a white solid. Remember before I had a dark red pungent liquid.
Mm-hmm.
Is this a chemical or a physical property?
It's a chemical property.
There we go. Oven cleaners contain sodium hydroxide, which converts the grease oil splatters to a water-soluble material, which can then be washed away. How many of you have ever tried to get rid of grease with just water? Can you?
No.
So if you can't do it, what is happening with the sodium hydroxide? Before I had grease, it wasn't water soluble. I add the sodium hydroxide, I get something that is water soluble. Is this a physical or a chemical thing?
Chemical.
So, has it happened yet?
Yes.
Yeah.
Has it, look, read the question.
No.
It hasn't happened yet. It just says it contains sodium hydroxide and the sodium hydroxide will convert it. Okay? I lost somebody. Jay Burns. Jay Burns, you there?
Yeah. Yeah.
A rubber band stretches when you pull on it. Is something different?
No, it's just physical. It's a physical property.
Physical property. Okay? An iron pan rusting in the sink. Rebecca.
Yes. Chemical change.
It's happening right now because it is rusting. So therefore, it's a change. It's going from iron into iron oxide. Hydrochloric acid has a pungent odor. Nathan.
Physical property.
Physical property. Hydrochloric acid will burn a hole in your jeans by breaking down the cotton. Come on, guys, answer it in unison.
Chemical property.
Chemical property, because it hasn't happened yet. Copper compounds have a blue color.
Physical property.
Physical property. Copper metal combined with oxygen to give a green color.
Chemical change.
Chemical change. Bread turns brown when it's put in a toaster.
Chemical property.
Physical change.
Chemical change.
I'm
Physical
going
change.
with chemical
Yes.
change. Because when you burn
says when,
something,
though.
you change it in some fashion. Is the burnt
But
part
it says when.
viable as bread is? So it's
No.
going to be a chemical change.
Why is it not property if it says when?
Okay. You're right. You're right. Sorry, Rebecca. You are correct. That is a property. That is a chemical property. Are we good, guys?
Yes.
Yes, yay. I have to find. My. Is it the first one? Yes, it is. Okay, we're going on to temperature, guys. 3 or 4 slides. It's not that much. Ladies and gentlemen, I will try not to use the F word in here. In other words, you can't see this, can you? Crap. And I just ruined a joke. I hate when I do that. I'll get it up there in a second. There we go. Okay, we'll move this here. Stop it. Okay. You can see that now? You can see that?
Yes.
Okay. 3 systems for measuring temperature. Fahrenheit. We don't use English measurements in here. So if you see Fahrenheit ever, change it to Celsius, or first thing you do is change it to Celsius. Understand, if I say Celsius or centigrade, it's the same term, same thing. Centigrade is based upon a value of 100. Kelvin is the absolute best temperature because basically what you're doing in Kelvin is you're comparing it to absolute zero. Kelvin conversion's very easy. All you got to do is take your Celsius temperature and add 273, or a more exact number, 273.15. So if you have Celsius, add 273 to it, you get Kelvin. If you have Kelvin, subtract 273 from it, you get Celsius. Now, Celsius, changing from Fahrenheit to Celsius, you take the Fahrenheit temperature, you subtract 32 from it, and you divide by 1.8. If you want to go the other way, you take 1.80, multiply it by the centigrade temperature, and add 32. Guys, how did they come up with the 1.8 and the 32? What does water freeze at in Fahrenheit?
32.
What's it freeze at Celsius?
0.
So immediately, you have to add 32 to the Celsius to get it to start at the same point. Now, do you know what water boils at? Hint, hint. Hint, hint. Boils at 212, right? Now, if you subtract 212 and 32, you get a division of 180 degrees. Water boils at 100 Celsius. So in Celsius, there's only 100 Celsius degrees. So to convert Fahrenheit to Celsius, you have to multiply the Celsius by 1.8. That's where that number came in. Sorry, I'm getting attacked by a Zoom. So, average body temperature is 98.6. Express this using Celsius and Kelvin. You got 1.8 times your Celsius plus 32 is equal to Fahrenheit, or the centigrade is equal to Fahrenheit minus 32 divided by 1.8. You do that math out, you get 37.0. So to get Kelvin, you got to add 273.15 to get, and you get 310.2. Questions about this? Okay. Next thing we're going to get into is density. Density are probably going to be the easiest problems you are going to deal with this semester. Basically, you have mass, density, and volume. You are either going to be given 2 of the 3, or you're going to be able to figure out a way to get 2 of the 3. All you have to do is realize what you do with them once you have them in your possession. For this, one of the ways to think about it is with the density triangle. You put the mass over the density and the volume. So if I have the mass and I have the density and I want the volume, I divide the mass by the density, I will get the volume. If I have the mass and the volume and I want the density, I'm going to take the mass, divide it by the volume, I will get the density. The third problem, if I have the density and the volume, I multiply density by the volume, I will get the mass. I can also use the labels. The labels will also help me figure this out. Okay, if the mass of the object is 35 and it takes 7 centimeters cubed of space, calculate the density. Okay, I have grams and I have centimeters cubed. The label for density is mass over volume. So if it's mass over volume, I'm going to take this 35 grams, divide it by the 7. When I do that, my label also divides grams by centimeters cubed. I do that math out, I get 5 grams per centimeter cubed. We good, guys? We good?
Yep.
If I have the mass and I have the density and the volume, if the density is equal to 1.52 grams per milliliters and I have 25 milliliters, I want to end up with grams. The way I end up with grams is I multiply the two of them together. 25 milliliters times 1.52 grams per milliliter. The milliliters cancel out. I'm left with grams. So my mass is going to be 38 grams. Last problem. If I need to find the volume, if my mass is 35 grams and my density is 1.2 grams per milliliter, what is the volume? Well, if I have my density at 1.2 grams per milliliter, if I take the reciprocal of that, my milliliters go on top, my grams go on the bottom. If I take the reciprocal and multiply the reciprocal by the 35 grams, the grams cancel out and I'm left with milliliters. I do that math out, I have 29 milliliters. Questions, guys? Gone through it quick? Anybody having any problems with density or had any problems in intro with density? Fairly straightforward problems, right? Okay. We're going to have our participants go on. Nathan, do the top problem. Aubrey, the middle problem. Blake, bottom problem. Dana, top problem. Dylan, middle problem. Jillian, bottom problem. Jasmina, top problem. Jay Burns, middle problem. Jessica, bottom problem. Joseph, top. Casey, middle. Rebecca, bottom. Work it out, guys. Okay, we good, guys? Those of you that did the top problem, what answer did you come up with?
1.2.
1.2.
1.2.
Good. The 7.5 limited your sig figs. Good. Those who did the middle problem, what answer did you come up with?
1.65.
What? I'm sorry, what'd you come up with? Did I hear you say 7.65?
1.65.
Okay, we got to figure out what did you do? How did you get that answer?
I took the 26.8 milliliters, subtracted that by the 23.7.
And you
I
came
got
up with what number?
5.05 milliliters.
Okay.
And then I took the
Wait. 26 minus 23 is 5. Sometimes, guys, when you're doing your answers, you got to look at the answer you get and you got to ask yourself, does this make sense? Dylan.
I did the wrong calculation. It's
Okay.
3.1.
Okay, 3.1. Now, what are you going to do, Dylan, to get your density?
8.32 grams divided by 3.1 milliliters.
And that ends up being?
.68 grams per milliliter.
Okay, are we limited by something, Dylan?
The 3.1.
So how many sig figs?
2.
So it should be?
2.7.
There we go. Last one, who did number 3? The last question.
I got 1.02 milliliter.
Bingo.
So did I.
You're on.
1.02, yeah.
Okay, stop share. I think I'm going to go on to dimensional analysis. I'm going to take things a little bit differently. If I can find the slideshow. Yeah, I have enough time to do dimensional analysis. This shows you that I am an English major, ladies and gentlemen. 'Twas brillig and the slithy toes did gyre and gimble in the wabi. All mimsy were the boar groves, and the mommy wrasse out grabby. Beware the
Can't see it.
jabberwock, my son, the jaws that bite, the claws that catch. Beware the jub bird and shun the frumious bundersnatch. He took his vorpal sword in hand, long time the maxome foe he sought. So rested he by the tum-tum tree, and stood a while in thought. And as an oafish thought he stood, the jabberwock with eyes of flame came whiffling through the togy wood and burbled as it came. 1, 2, 1, 2, and through, the vorpal blade went snicker-snack. He left it dead, and with its head, he went galumphing back. And hast thou slain the jabberwock? Come to my arms, my beamish boy. O frobbiest day, caloi calais, he chortled in his joy. 'Twas brillig and the slithy toes did gyre and gimble in the wabi. Oh, mimsy were the borogroves, and the mommy wraths out grabby. I love that. Ladies and gentlemen, there are 20 tum-tum trees in the togy wood. In each togy wood is one frumious bandersnatch. There are 5 slithy toves in 2 borogroves. 2 mommy wrasse per jabberwock, 2 jub birds in 200 tum-tum trees. There are 200 mommy wrasse in each borogrove and 5 jub birds per slithy tove.
Professor,
Yeah.
we can't see your screen.
Ah!
I was trying to tell him that.
You could have stopped me in the first stanza.
I want to interrupt your poetry, you know.
Ah. Share screen. Why is this not in here? I cannot figure out why I can't do this. There we go. Now do you see it?
Yes.
Yes.
Yes, okay. There are 20 tum-tum trees in the togi wood. In each togi wood, there's one Fermius bandersnatch. There are 5 slithy toads in 2 borogoves, 2 mommy rats per jabberwock, 2 jub-jub birds in 200 tum-tum trees. There are 200 mommy rats in each borogrove and 5 jub-jub birds per slithy toad. If I had 5 Fermius bandersnatches, how many jabberwocks should there be? What do I want to know, guys? What answer do I want to know?
How many jabberwocks there is out of, if we had 5, whatever.
So
Matchers.
whatever you know goes on the left side of the equal side. What you want to know goes on the right side of the equal sign. So I have 5 BSs and I gotta end up with JWs, right? Do I have a conversion factor for bandersnatches with anything else?
Tuglywood.
Tuglywood. So there is 1 Tuglywood for every 1 bandersnatch. If I start off with 5 bandersnatches, does the Tuglywood go on top or does it go on the bottom?
Top.
It goes on top, bandersnatch goes on the bottom, so that when I multiply them, the bandersnatch label goes away. Now we got Tugglywoods. Do we have any relationship, Tugglywoods, with anything else out there, ladies and gentlemen?
Tum-tum trees.
How many?
20.
So I just turned my bandersnatches into Tugglywoods. Do I put the 20 on top or do I put the 20 on the bottom? Look at your labels. I have Tugglywoods. I need to turn them into tum-tum trees. What goes on top?
20.
20 tum-tum trees go on top. The 1 Tuggywood goes on the bottom, so it can multiply with the Tuggywood I have, and it gets canceled out. Now I have tum-tum trees. What am I going to relate those to?
2 jub-jub birds.
What goes on top?
The 2.
2 goes on top. 2 jub-jub birds goes on top. 200 tum-tum trees go on the bottom, so that it cancels out. Now I have jub-jub birds. What do the jub-jub birds turn into?
Slithy toves.
Slithy toads. Okay. Then what do the slithy toads turn into?
Burrow groves.
Borogroves. So what we're doing, ladies and gentlemen, what you are doing is you're systematically going from one label to another, to another, to another, until you end up with the 2 mommy rats per jabberwock. And since you want to end up with jabberwocks, the jabberwock goes on top, the 2 mommy rats go on the bottom. So, are we good with this? So I got 5 bandersnatches. times 1 togi wood per 1 bandersnatch times 20 tum-tum trees per togi wood times 2 jub-jub birds per 200 tum-tum trees times 1 slithy toad for 5 jub-jub birds times 2 borogroves for 5 slithy toads times 200 mommy rats per borogrove times 2 jabberwocks for 2 mommy rats. I do all that math out and I get 8 jabberwocks. I illustrate this, I use this absurd example to illustrate that you don't even have to understand what you're dealing with to do dimensional analysis if you keep the labels. Remember, the labels are your friends. The steps, you got to figure out, what do you want to know? You got to figure out what's given to you. You got to figure out what you do know and map out a solution. Establish the conversions. Last step is doing the math. So, my house has a backyard, 100 feet by 500 feet. What is the area in square meters? The what I want to know is the square meters, right? But what do I know? What do you have in your background?
Feet.
Feet? Okay.
You have square feet?
How you get square feet?
It's in the question. It says that your house has a background that measures 100 feet by 500 feet.
So what do you have to do?
Multiply the
Convert
feet.
it.
You have to multiply them, right? That's knowledge you already have. So you multiply 100 by 500 and you end up with 50,000 square feet. Now, what do we have to do from here? We have to go to step 3. We have to figure out conversion factors. Basically, guys, you're either going to know them, they're going to be given to you, or you can look them up. Okay, somebody asked in the forum about conversion factors. I will try to give you everything you need, but some things may elude me. Like, for example, how many days in a week? I figure that's a pretty solid one that you all should know. How many days are in a week, hours in a day, minutes in an hour, and seconds in a minute. Some of those are things that are just so obvious that it may elude me. If you need something, give me a call during the test. I promise during the hours of 5:30 to 7, I will be right here. So if you need to question, feel free to give me a call. Just talk to the proctor, say, Proctor, I'm sorry, but I need to call Mr. Popovich. So we have a conversion factor. We want to go from square feet to meters. Okay, how are we going to do that? We have square feet. Joseph, I have square feet. I want to get to meters. What would the first step be?
To turn it into inches.
Turn it into, how are you going to do that?
Well, I mean, it says right there, 1 feet is 12 inches.
So how are you going to do it? You have 50,000 square feet.
50,000 and you like times, and then you do 12 inches over 1 foot. Is that what you're talking about?
How many feet did you cancel out?
1.
Feet squared, how many do you have?
Oh. I'm confused.
Okay, let's look at this. I'm mapping this out.
5.
If I just do it once, right?
Okay.
Understand this is feet by feet, right? If
Again.
I just do inches over feet once, I only cancel one of those feet and my label becomes foot inches. Does that make sense to you, Joe?
Yeah, I got it. I got it now.
So I got to do it again. Then once I have the inches squared, I got to do my meters over inches and do it again because I have inches squared over there. So I'm mapping out my solution now. Basically, guys, if you start off with English and you want metric, eventually you're going to have to use a conversion factor of metric to English in one fashion or another. If you want to end up with metric, the metric unit goes on top. If you want to cancel the English unit's going to go on the bottom. And vice versa. If you start metric and want to end up with English, English goes on the top, metric goes on the bottom. Okay, so I don't know what I did here. Okay. So I'm at this step. I've got my map. At this point, all I do is plug in the numbers from the conversion. Put the 12 inches over the foot, 12 inches over the foot, 1 meter over 39.37, 1 meter over 39.37. I've got my problem solved. My feet cancel, my inches cancel. I'm left with meters times meters. I am left with the correct label. Then all I have to do is do the math. I do the math and I end up with 4.65 times 10 to the third meters squared. Questions? Fort Knox has 147.3 million ounces of gold. If my Ford Ranger can haul out 1 ton per trip, how many trips will it take for me to steal all the gold in Fort Knox? Not that I haven't thought about that. So what do we want to know? We want to know the number of trips. The number of trips is going to go on the right side of the column. So how are we going to end up doing this problem? Jay Burns, give me a start. Tell me where I'm starting from.
So you're starting, you have to take 1 ton.
Go on, Jet. Go on.
Okay, so you'll need conversion for ton to ounces.
Okay, do you know anything about tons?
It's 1,000 pounds.
How much?
1,000?
2,000.
2,000.
Okay, so what you're doing is you're going from your answer backwards. So you got 1 trip over 1 ton. Then you got that equal to 2,000 pounds over 1 ton. So now I've worked it out where I'm up to pounds. Do you know the relationship between ounces and pounds?
I don't off the top of my head.
Is it
16 ounces
16?
per pound. So if I have the ounces on top, then or the pounds on top, I get 16 ounces per 1 pound, or I'm sorry, 1 pound per 16 ounces. And I'm left with my 147.3 million ounces of gold. So if I'm mapping out my solution, I have ounces. I'm multiplying pound by pounds over ounces times tons over pounds. This will give me my number of tons. I do this math out, and I end up with 4,603 tons. So it's 4,603 tons times 1 trip per ton. This gives me 4,604 trips. Because 4,603 won't get it all out. There's a little bit left over. So I have to make one more trip. Guys, this is very important. Your labels are your friends. Your labels are your friends. When you do the problems, cross the labels that cancel. That way, it's going to make you avoid silly mistakes. The labels will prevent you from dividing when you should be multiplying, and multiplying when you should be dividing. Questions about dimensional analysis, ladies and gentlemen? Some of the problems can be a little bit difficult. One of the problems in the homework was changing miles per hour, or was it centimeters? Was it centimeters per second to miles per hour? Yeah. You have that. You have centimeters per second, and you want to change that into miles per hour. How are you going to go about and do that? The easy way to do that. First thing you do is you take your centimeters, change it into miles. You then take your seconds, change it into hours. Then you have your miles and you have your hours. Just simply divide your miles by your hours. Questions, ladies and gentlemen? Are we good, ladies and gentlemen?
Yes.
So do sig figs count?
Yes.
So are you going to give us like the exact value? Because like, say like 1 kilogram is like 2.2 something pounds. So do we just use 2.2 or do we use more sig figs?
Depends upon what the original weight was.
Okay.
If I give you a number, 3.85 pounds, you can't use the 2.2. I will have to furnish you with a more accurate conversion factor.
Gotcha.
And guys, I'm not going to give you I'm not going to mess around with you. I'm not going to give you 2 conversion factors and have you choose between which one's the right one. I'm not going to do that here. Okay? That's something that will be given to you on a test. And again, if you find that you need a conversion factor that's not there, if you're taking the test between 5:30 and 6:45, I guarantee you that I will be here. If it's at some other time than that, then there are chances that I won't get to it. Okay, let's see if I have my I have not talked about matter yet, have I?
About what?
Matter. What's the matter? The jokes don't get any better, guys. Nope, I don't want to do that. Why do computer, somebody explain, if you explain this to me, I'll give you an A right now. Why do computers do what you tell them to do rather than what you want them to do?
They can't read your mind yet.
That's a simple matter.
I like that one.
Okay. Basically, we're going to go through this. How many of you have had this stuff in 6th grade science or even before that? You've had it in 9th grade chemistry, and then you had it in junior level chemistry, right? We always start with matter. 2 characteristics, guys. It has volume and it takes up space. Right? No, that's just one. It has volume and it has mass. Those are the only 2 characteristics. Now, I know somebody out there is going to say that there are more than 3 states of matter. But we're going to just deal with the 3 states: solid, liquid, and gas. We're going to forget about plasma, and we're going to forget about the other thing. Big question: what makes up matter? Anybody?
Atoms.
Atoms.
Okay.
And atoms are composed of elements. An element is a substance that cannot be broken into simpler substances by normal chemical reactions. And what composes elements? There we go with atoms. What is an atom? It's the smallest identifiable unit of an element. And as I said, we have 3 states: solid, liquid, and gas. We are not going to get into plasma. And there's another one out there that I can't even remember off the top of my head. We're just going to deal with solid, liquids, and gases. We're going to stay on the planet Earth. Now, the difference between the 3. When you have a solid, you have the atoms that are very, very closely packed to one another. They're very, very dense. They're very, very rigidly held. When you have a liquid, they are less rigidly held, and you have the molecules sliding over one another, which allows them to be poured. They're less dense than solids, but very, very much more dense than gases. Gases are their own free agents of the world. A gas can do anything it wants. It has no fixed volume. It has no fixed mass. Again, nothing more. These next slides are doing nothing more than what I've already told you. This is the slide that's important. Solids have a definite shape, definite volume. Liquids have a definite volume, but the shape is going to be the shape of the container. Gases, all bets are off. They take the shape of the container, they take the volume of the container. Now, we get into classification of matter. Another way to classify matter is if all of the atoms in the sample are the same, we have a particular type of matter called an element. We also have some things called compounds, and compounds are made of atoms of 2 or more elements that are combined in the same manner. This is where we get into the law of definite proportions. The law of definite proportions was written by Joseph Proust in 1797. Mr. Proust, in addition to discovering oxygen, came up with this particular law, and he basically said, if you have one compound, the ratio of the different atoms within that compound will always be the same. If I have a water molecule, it will always have 2 hydrogens and 1 oxygen. If I have a methane molecule, it will always have 1 carbon and 4 hydrogens. If I have a glucose, it will always have 6 carbons to 12 hydrogens to 6 oxygens. And I just noticed that I'm a little bit over the edge here. Anybody have any questions? I've gone through this fairly fast, guys, mainly because of the fact that that was one of the critiques I got in the summer, was the fact that I languished on this stuff, and they said they didn't think I had enough time for the later stuff. Questions on today? Pretty much review of what we've done, what you did last year?
Yeah.
Okay, questions on anything else?
Don't forget about accessibility services.
Thank you. Thank you very much. Guys, something I forgot when I was talking about the syllabus. If you have a disability, then first of all, you got to send the letter to me. And I don't believe I've gotten any letters so far. But please do me one favor. I will be happy to accommodate you for the extra time that you need. But what I do need is for you to help me out and just remind me, especially for the first test or the first two tests, that you do need this time. I'll be happy to give it to you just about a week beforehand. Just tell me, hey, Mr. Popovich, remember to give me extra time. Be happy to do that. Something else I want to ask. Would anybody be overwhelmingly not hurt, but anybody be overwhelmingly bothered by the fact that I move the time for the lab on Tuesdays back 15 minutes? I've got a problem, ladies and gentlemen. The problem is when I record this, when I end this recording, it has to load up into the, it has to load up into my computer. So it has to download it. It takes some time to do that. So it has to download that. And then what happens is I can start another recording. If it's downloading while I try and record another thing, it throws this thing into a tizzy. And basically, I was not able to record the meeting for the laboratory on Tuesday because of this. So if we can move the lab meeting back 15 minutes, I would appreciate it. Other than that, Mrs. Lincoln, how did you like the play? That's my favorite joke. You see, Abraham Lincoln was dead. He got killed.
That's a low blow.
And because he was dead, it kind of ruined the evening for Mrs. Lincoln. But other than that, anyway, guys, I will see you on Tuesday, okay?
Sounds good.
All right. Have a good weekend.
You have a
See
good
you
weekend
guys.
too.
Bye.
Can I ask you a quick question on the
Yeah,
lab?
I'm here. I'm here. Go ahead, Dylan.
So I'm doing the summary of experiment for the chemical and physical changes and properties lab.
Okay.
And I was
summary.
wondering, how long do you want them to be?
Whoa, what are we talking summary? I'm not on, are you talking about the notebook?
Yeah.
Okay, I believe I called it a results section, Dylan. Summary's okay. I don't care what you call it, as long as you put it in there. How long does it have to be? You have to, the first sentence of the summary has to answer the question of the objective. So that's a one sentence thing. For example, when we're doing the density, we're going to be doing densities of solids and liquids. You're going to say, okay, the density of my solid was this, the density of my liquid was this. All right? Then you have to go into an error analysis. And basically, you have to think, and you have to look at the experiment, and you have to see what went wrong. Okay? I spilled some liquid out of my, I spilled some liquid onto the balance, and therefore my weight was too big. Okay? Are you with me, Dylan?
Yeah, thank you.
Okay, now, not only do you have to identify what you did wrong, you have to identify how that would have affected your results. Putting the liquid on the balance pan would have given you a weight that is larger than the weight that's in the graduated cylinder, right?
Yeah.
So you are dividing the weight by the volume, so therefore your density would have been larger than it was supposed to be. That's what I'm thinking, okay? How long?
Okay.
Paragraph or so.
A paragraph or so. All right. And then we just tape in our data table before our calculations.
Yes,
All right. Thank you very much.
no problem. That's what I'm here for, Dylan.
Have a good weekend.
You too.